We will compute orders of some element. See, in any finite group G, if G is a finite group, and G is an element in G, it is most important to decide what is an order of G. Order of an element G which I will denote odd G. This is the smallest, this is the minimum, this is the minimum of m in n star such that G power m is identity. The first time when it becomes identity. Obviously such a minimum exists because obviously if I start with G, G square and go on, all these elements cannot be different because G is a finite group. So there will be two of them, at least two powers will become equal. So Gm will be equal to G power n, and then whichever is the less power I will multiply by the inverse of that, and then I will get G m minus n is definitely identity element. So there exists at least one non-zero natural number for which the power becomes identity, and such a power, the minimum, is called the order of an element G. So for example, let us compute some order of some permutation. So for example, if I take a transposition 1 2 in Sn, this means only 1 and 2 are moving, remaining integers are fixed. If I call this as rho, what is rho square? Rho square is by definition rho compose rho. That means I have to compute this, I have to know what is its value on 1 and 2, because remaining element are fixed under rho. So I do not have to worry about other than 1 and 2. And at 1, where does it go? So rho compose rho at 1 is by definition rho of rho 1, but rho 1 is 2. So it is rho of 2, which is 1. Similarly, rho square of 2 is by definition rho of rho 2, which is rho of 1, because 2 goes to 1, and rho of 1 is 2. So rho square of 2 is also 2. That means on 1 is identity, on 2 is also same thing. That means we have proved rho square is equal to identity map, because all other elements are fixed under all. So therefore the 2 cycle has order. What we have checked is rho is not identity and the next power is identity. So that means what we have checked is order of rho in the group, permutation group, is 2, and nothing special about 2 cycle. Even if you do 3 cycle, let us say 1 2 3, if this was rho, I will ask you to check rho cube is identity. That is very easy to check. You just have to check on 1 2 3, because remaining integers are fixed. So you have to check rho 3 of 1. Rho 3 of 1 is rho square of rho 1, but that is rho square of 2, that is rho of rho 2, but that is rho of 3, that is 1. So it is fixed under rho 3, rho power 3. Similarly, check that rho cube on 2 is 2 and rho cube on 3 is 3. So therefore the order of rho cube is 3. You have to check that rho square is not identity, but that is very easy actually. When you are given a cycle like this, what you do is, if you want to write rho square, you jump. So 1 has to go to 3, 3 is going to 1, but you have to jump 1 step. So 3 goes to 2, and 2 goes to 3, but you jump 1 step. So this is the cycle. This is rho square, and rho cube you will order like that, jump. So similar thing. So I will not, let me not calculate things. So that is how one calculates the powers quickly. So, in general, if I have a K cycle, I1, I2, IK, K cycle means the cardinality of this support is K. If this is rho, then rho power K is ID. This is in general we have to check. And how do you check this? You just check that on all each I1, I2, IK they are identity, they are fixed, and others which do not appear here they are automatically fixed under rho, therefore they are fixed under rho power K. So, K cycle will have order of a K cycle is K. Order of a K cycle rho is equal to K. That is the number of elements in this is number of cardinality of the support of rho. So, once you have this, then given any permutation sigma in Sn, we have canonically decomposed this sigma into R factors, sigma 1 to sigma R, where these guys are cycles, disjoint cycles. And use of disjoint is because they commute with each other. So, therefore, if I raise it to power, so I want to claim that order of sigma is nothing but LCM of the orders of sigma 1 to sigma R, and I know this order because it is a cycle. This is equal to cardinality of the support. So, that is the formula for the order. And how do we check this equality here? Because if you have LCM, then you raise it to this equation to power L, that is sigma 1 to sigma R power L, but because they commute I will take this L inside. This is sigma 1 power L, sigma R power L, but this L is a multiple of the order, therefore already that will become ID. This is become ID, next will become ID and so on, next will become ID. So, this is ID. So, that shows that the LCM is, and smaller will not work because, so L is the order of sigma. So, nice formula. Order is computed by using the LCM. Of course, one needs to calculate LCM. So, LCM is computed by using the prime decomposition, which I will not address here. Of course, okay. So, we know, so therefore, to each permutation sigma, we have attached an integer which is the order sigma. Now, I also want to attach another, I want to attach a sign, SIGN sigma. This should be an element in plus minus 1. And how is it attached? So, first I will write down for a cycles, what happens to the cycles. So, for example, if you have 1 2, this is a transposition. So, this should be the number. So, given any permutation sigma, I want to decompose this into cycles, transpositions. So, tau 1 to tau r transpositions, and count how many are there. There are transpositions. Obviously, this decomposition is not unique anymore like a canonical decomposition, because what might happen is somebody might insert here 1 2 and 1 2 again. This is identity actually. So, I have inserted identity, but it is this. So, I may club So this decomposition is not unique, the number is not unique, but the parity is unique. This is what I want to prove. So to do that, sigma is obviously product of transposition, because for that I just have to write every row is every cycle I1 to Ik. This is a product of transposition, because if I can do that, then already I know sigma is a product of disjoint cycles, and each cycles I will decompose into transposition. So altogether each sigma I would have decomposed as a transposition, but I cannot claim any more uniqueness, because this, when I decompose even the cycle into transposition, that decomposition is not disjoint anymore. For example, this one is I1 I2, I2 I3, we will check this equality and so on. The last one is Ik minus 1 Ik. Now to check these are equal, these two products are equal, let us check that. So I only have to check that what happens to the images of I1 to Ik under row on both sides. Well, the left side I know I1 goes to I2. This is LHS. And let us check now RHS also. I want to check that I1, where do I1 go? Let me check that where do I1 go. Now here, see, remember we are applying this first, then this, then this, then last is this. So under this I1 is fixed, because they are different elements. So I1 is not one of them, so I1 is fixed here, I1 is also fixed here, here also fixed, only I1 is moving under this first transposition, and there I1 goes to I2. So the result is same. Now let us check where I2 goes. Here I2 goes to I3 on the left hand side. On the right hand side, see, as long as you don't reach here, all these keep I2 fixed. The first time I2 moves is this transposition, and then I2 is moved to I3, and here I3 is fixed. So I2 goes to I3, which is also here. And similarly all other things, I3 will go to I4, same reason. Last one Ik will go back to I1. Let me check only the last one. So where do Ik? Ik goes to Ik minus 1 here. Ik minus will go to Ik minus 2, and so on, it goes backward. So I2 will go to I1, so Ik will go to I1. So therefore we have checked that every k cycle actually we can write it as a product of how many transpositions? 1, 2, k minus 1. So what we have proved is every, I will write the result, every k cycle is a product of k minus 1 transpositions, and not necessarily disjoint. In fact, not disjoint at all. You see here this cycle and this cycle, they have I2 in common. The next one I3 will be common, and so on. So they are not disjoint, and because they are not disjoint, you cannot demand uniqueness. So once every k cycle is a product of transposition, then every sigma is also product of. Therefore every sigma is also a product of transpositions, because you take sigma, write sigma as a product of disjoint cycles, and each cycle you decompose into k minus 1 transpositions. So each sigma will be a product of transposition. Now our problem is, how do you decide how many? And the only thing you can decide, they are either odd or even. So that is what we want to prove now. So this is a temporary definition I wanted to prove, temporary definition. I wanted to write sine of sigma is 1 if sigma is a product of even number of transposition. And minus 1 if sigma is a product of odd number of transposition. Now we have to check that this definition makes sense. So that means what we will have to check? We will have to check that if somebody writes sigma as a product of even number of transposition and somebody else also do it in some other method, then the number should not change from even to odd. That means the parity should be same. This is the problem we want to check. Either do that or don't define this way, define it in some other way and check this. So I prefer to do it the other way. I will define sign which will be canonical definition, and then we will check that this parity will remain the same. So the proposed, this is not, I do not want to define this way. So I propose a definition given sigma, I want to define sign. So define sign sigma by minus 1 power n minus s, where what is s? Where s is the number of equivalence classes of the relation, equivalence relation, this sigma. Let us, what is that? That means we have decomposed the set n star n into exactly s pieces, I1 union is. Some of them could be singleton and some of them are not singleton, and only the non singletons will give you a cycle which is in the product of sigma, and this decomposition is very canonical. It uses only a permutation sigma and nothing else. So let us first analyze this definition, what it is. All right. So this is called the signature of sigma. Let us write more precisely. So what we have done, we have this n star n, we have decomposed into, let me now write IR union I1 disjoint union I2, this disjoint union IR, this gives the cycle sigma 1, this gives the cycle sigma 2, this gives cycle sigma r, they are not singletons, and then the start singletons union IR plus 1, disjoint union always, union IS, and these guys are singletons. So they do not contribute to the cycle decomposition. Canonical cycle decomposition is this sigma 1 to sigma r. They do not appear because they correspond to the identity. Okay, and then what do we know from this? Because this Cartesian, this set has partitioned into several pieces. So definitely we know cardinality of n star n, is cardinality which is n, is broken into so many cardinalities. Cardinality I1 plus cardinality I2 plus cardinality IR plus now 1 1 1 1, how many times? Plus r minus s, s minus r. S minus r. That is how the cardinality n broken into the pieces. Okay, therefore what is minus 1 because of this, what is minus 1 power n minus s, this is equal to minus 1. Now n I will put it from here, and this s is getting cancelled with this. So, and then this r I will distribute 1 among each one of them. This is minus 1 power cardinality I1 minus 1 plus cardinality I2 minus 1. I have just broken, I am just writing n minus s plus cardinality IR minus 1. This is same as this plus, and this minus 1 will come exactly r times, that is, and this s is I have shifted to this side. So, this is same as minus 1 power cardinality I1 minus 1 minus 1 power cardinality I2 minus 1 cardinality. And so on, minus 1 power cardinality IR minus 1. Therefore, then this was my definition of a sine of sigma. So, therefore, we get a formula sine of sigma equal to product I is from, or k is from 1 to s minus 1 power cardinality I k minus 1. You see, note here, when you go for the singleton, this does not contribute anything. So, therefore, what is this? Therefore, signature is the number of orbits of even cardinality. So, sine of sigma equal to minus 1 power m, where m is the number of equivalence classes of cardinality even, because if equivalence class has cardinality odd, this becomes even and then it goes, it does not contribute anything. So, that is the formula. Now, if you compute, let us say rho, if rho was a cycle I1 to Ik, this is k cycle, then what will be the partition corresponding to rho? There is only one equivalence class which is the whole thing, and the remaining guys are singletons because they are fixed. So, therefore, this has decomposed this n star n into only one, in this case r equal to 1, and that set is I1 to Ik, this is, and union the complement of this singletons. So, this goes then union singleton J1 union disjoint union J, how much? Jn minus k, they are all singletons. So, they do not contribute anything to the canonical decomposition, only this is computed in the canonical decomposition, and we want to compute how many equivalence classes are of cardinality even. Well, these guys are singleton, so they are cardinality odd. So, these do not contribute anything to M, and this one depending on n is even or odd, it will, so this then sine of this rho will depend minus 1 power the cardinality here. If this if k is also odd, then this is also odd cardinality. So, this also do not contribute because minus 1 power this will be even. So, it will not contribute. So, only contribute when k is even, and then here it will come minus 1 power the cardinality here, that is k minus 1. Minus 1 power 1 actually, why k minus 1? Minus 1 minus 1 if k is even. If k is even, that means this cardinality is even and there is only 1. So, m is 1 in this case. So, in this case m equal to 1. So, 1, this is minus 1. So, what you have noted is if this k were even, then the sign is minus 1. For example, test it for the transposition 1 2, k is 1 in this case, k is 2, and what you wanted to know how many equivalence classes of cardinality even, only 1. So, m is 1. So, sign of a transposition is minus 1. Sign of a 3 cycle, this is k is odd. So, the equivalence class minus 1, the even that will be, so this is 1. So, this is very easy to compute. You just have to see what are the equivalence classes, what are their cardinalities, and if cardinality is odd, forget them. If cardinality is even, you count them how many equivalence classes are of cardinality even, and that number is m, and then put minus 1 power m, that is the sign. And now the biggest thing, the most important thing we need to prove is this will not change. So this is the theorem we need to prove. Theorem we need to prove is, if sigma is the permutation, and if suppose somebody writes sigma as a product of k transpositions, then I want to prove that where tau 1 to tau k are transposition, may not be disjoint, then I want to prove this k is nothing but no, not k. I want to prove that sign of sigma is minus 1 power k. This is what I need to prove. So, if k is even, this will be 1. If k is odd, this will be odd, minus 1. This is what I need to prove. Or equivalently, okay. So, we will prove this first. Let us prove this first. So, proof. I am going to prove this assertion. See, remember, what is most important to note is this tau 1 to tau k may not be disjoint, because if they are disjoint, there is nothing to prove. So, note tau 1 to tau k need not be disjoint, and that makes more complicated to compute. And this formula I want to check by induction on k. On k. So, start when k equal to 1, sigma is a transposition, and then we have checked the transposition as sign of transposition is minus 1. So, induction starts. Therefore, to simplify the notation, I only have to check only to prove if I have arbitrary permutation and if I have one transposition, tau is a transposition, that is which maps I to j and j to I transposition, then I will have to prove a formula sign of sigma tau or tau sigma equal to minus sign sigma. So, one at a time I will remove. So, this is what I have to prove. That means I want to show what, how do I show this? That means I want to show that the number of orbits of tau sigma and sigma, they differ by 1. So, I will compute the orbits under sigma and orbits under tau sigma and check that they differ by 1, and therefore, the sign will differ by -1 power 1, which is -1. So, I will leave it for you to check this. This is very easy. Okay, so we stop this, and next time we will introduce multilinear maps and alternating maps.